Okay, hello. Oh, hello. Oh, wait. Oh, I'm sorry. That
Good
is
morning.
sorry. Oh my God. Okay, sorry. That is quite a reaction. Well, we're starting that is not sorry, not totally on purpose on my part. Wait, wait, wait. I'm coming. I'm here. It's not one of those. Wait. Oh, how do you? Wait, I'm sorry. How do I stop this? Wait, I'm sorry. Okay, okay.
I think you have, oh yeah.
Yeah, okay. Sorry, it was a little bit okay. I'm trying to take a page out of your collective book, not you, Gabrielle. Good morning, Gabriella, and good morning, Jocelyn. Good morning, Sydney. I guess I'm taking a page out of Sydney's book. Good morning, Melanie. And I'm not at all doing it for the sake of faculty meetings on Zoom. Oh, yes, I totally am. Okay. Anyway, um, um, um. Okay, but yes, thank you. Okay, good morning, good morning. What I said, Gabriella, Jocelyn, Sydney, Melanie, good morning, Sinead, who else? Sinead, and sorry, Sinead, you are all set again with the re-login stuff, right? In fact, I should check. I'm a little worried. I know this is like a personal thing. I know you had a login thing. Hold on, but are you doubly logged in now? Sorry, one second. No, I think it's fine. Okay, I'm fine if you're fine. Okay, I'm gonna go on. Tell me if there's a problem, shit, but I'm thinking you're fine. Um, more people coming in. We're start. Chat. Yes, good morning, Melanie for the double. Good morning, Sinead for the double. Good morning, Lunar. Good morning, Teresa. Good morning, Jocelyn for the double. Good morning, Genesis. Good morning, Sydney for the double, triple. Um, Double. Good morning, and the inspiration. Good morning, Nadine. Good morning, Jean. Good morning, Joshua. Yeah, okay, good, Sinead. Thank you. That's closing a conversational path. You should submit points for that. Seriously, because it calms my soul, which we all need, which we all know needs all the help it can get. Good morning, Chanel. Okay, wait, more people coming, and we'll start. Okay, and I'm gonna quickly say. I know this is I always over. Your exams are happening. They're not forgotten, I promised. I move very slow on this for 1,000 and I travel a lot, whatever, but like I'm in them. So you're gonna start seeing them land in your you in dribs and drabs. You're not all gonna get them at the same time. Just when I finish one, it'll drop. Some of them I actually, when I finish one and feel like I can put a final grade on it, it'll drop. So I'm not trying to get you. I just want you to know they're not forgotten. And they just go very slow, and I apologize, but they're happening. And oh, and on that, so I'll just keep talking. So we're just going to keep proceeding. And certainly the bottom line is, even though I do take too long on them, you will certainly have them and feedback. And there's feedback. They're not just like, oh, I mean, that's why they take a while. And the idea behind them is so that you know what better to do for the final exam, which is formatted very similarly. Like, okay, so just anyway, so you certainly have them before that, like, is an issue. Um, I'm glad we took it a little anyway, but on that also, because I know it's like annoying, believe me, I know. Sorry. So on that topic, you may notice that I readjusted some of the homework dates or I adjusted in Google Classroom, and they might be adjusted again. In other words, I think there was a homework that's supposed to be due in 2 days. I changed it to next Monday. Just look, you'll see. I guess that's the bottom line. If you and some of you already even turned in that homework, which is phenomenal, but not an expectation, and would be hard to do unless you had some background or whatever. Bottom line, just check the homework dates. I'm checking them too. And as always, as long as you turned in a recent homework, a thorough attempt on time, then if you think you rocked it and I didn't give you any feedback and it feels like what we're saying in class confirms that you rocked it, just resubmit it and you'll get more people are doing that. I'm glad you understand that. But if you're seeing things in class that are happening that are helping you revise it, then just go straight to the revision stage and it's easier for me to look more closely at the revised versions because they're better and there are fewer of them, etc. So I think I think this class really gets all that, and I appreciate it. I just to say, there's still time for all of us to catch up with each other. Okay, sorry, someone's here. Okay, good morning, Jibo. Thank you, Effie. I'm not even sure what you're. Wait. Sorry, she's talking to, or I mean, sorry, they, everybody. Okay. Good morning, Mohammed. Good morning, Effie. Right. Good. I guess that counts as multiplayer co-op, Mohammed and Effie. Okay, nice. You guys, I'm going home. Okay, good morning, Zebo. Okay. Have I mentioned that my 11-year-old son recently discovered the splendor that is South Park? And oh yeah, it's a family dilemma because how do you keep someone away from anyway, okay, let's go. Let's go. Physics. So I'm going to continue right now with Newton's law, with the whole issue on the table now is, yeah, no, it's true. I can't even, I mean, this is not a paid advertise. In fact, I can't even, but yes, I agree with what's in the chat. Um, um, and I have not seen the recent stuff that's supposedly even over the top by their standards about the white, like I'm not even commenting on that. Okay. Um, Um, quick context, like what are we doing right now? We're deep in Newton's second law. Like all the problems on that most recent homework sheet that I'm still in the mid homework 7, which I'll screen share in a second. Like it's all about using Newton's second law to solve problems, right? Again, quick summary. What is physics about? Predicting where something is going to be when. That's it, right? Where a certain point of mass, at what point in time will it be at a certain point in space? Or at a certain point in time, what point of space will it be? Or for you guys, if you're using, that's classical physics, predicting trajectories of particles. Where's this ballistic going to be when, or I shouldn't even, or where's this planet going to be when, or whatever. But then for you guys in the modern day, in the 21st century, what are you doing? Most of you are using physics in order as a foundation for your forensic pursuits, maybe even some of you in criminalistics, right? So you're using physics to retro, or you're learning physics so that ultimately you see the practices and principles by virtue of which we can retrodict where something was when, right? A given point of mass at a certain point in time in the past, what point of space was it? Where did the bullet come from? Where did the blood spatter come from? Where did the car collision occur? Like it's right. Just so you know, like that's what this is all about. Physics is where is something when. That's it. That's all there is to physics. Mass, space, time, or well, stuff in space and time. Maybe the stuff can get more abstract than just mass. Physics 204. But that's what it's all about. So the first part of this whole course was like realizing the way we do that is by virtue of acceleration. The thing to know about a particle at a point in space, at a point in time, is its acceleration at that point in space. It's instantaneous. It's second derivative of position with respect to time, hence the calculus. If we know the second derivative with respect of position with respect to time, then we can predict the future or retrodict the past. That's the idea of the first half of this course and the first development in physics. But the next idea is, well, how do you know its acceleration? If acceleration is an effect, what's the cause? The cause is the sum of all of the forces acting on a particle. Okay. So now what we're doing is saying, given a bunch of forces acting on a particle, on a point of mass, whatever, given a bunch of interactions that are occurring, can we compute the acceleration and thereby predict or retrodict the motion? That's the game. Again, remarkably not easy, but remarkably simple. Okay, so now it's all about the forces and the whole law that takes us all the way, like forever in physics in a way. I mean, it gets adjusted by Einstein and stuff in the 20th century, and that's all super cool. But fundamentally, at the heart of physics, forever is F net equals ma. The sum of the F's equal the ma of a particle. That is like forever at the heart of physics. It's how we put people on the moon, well, honestly. Even though by the time we put people on the moon, we had already had Einstein and all these like cool modern expansions, but still, it is Newton's second law and some other laws of Newton that, so this is not small. So what I'm here to say, and I'm going to go back to I'm going to get concrete in a moment, truly. What I'm here to say is the whole thing is about F net equals ma. So what that really means to a physicist, what that really means to us, is it's all about what are the F's that are being added together on the left side of F net equals MA so that we can get an A. That's where all the thought, because the math is not the issue of this. Like, seriously, I've said that before. It seems like it would be, but it's not. The issue is setting up the math, which means knowing what to put on the left side of F net equals MA, which then know what I'm saying, and then is that means drawing diagrams. If you really, and I want to emphasize this a lot, because again, I swear to you all, I don't know why I'm all fired, like, I swear to you all, for the longest time, vector diagrams and then free body diagrams, which is what we're talking about at force diagrams, I really misunderstood and thought, like, when I was in college, I thought force diagrams were like sketches to give you an idea of what was going on. I thought they were like a helpful, like, student tool to be like, here, welcome softly to the physics problem. Let's get a sense. And now let's solve the physics problem. I didn't understand. Like, no, 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 no. The diagrams, if you take them seriously, if you actually follow the rules of diagram drawing, then the diagrams do the work for you. They're not rough senses of visualizations of what's going on. They are computational tools, like, truly. Same way vectors are. That lab 3 is meant to show you if you actually draw vectors to scale, they are a calculator on it. Okay. So what we're learning now is literally how to set up diagrams so that by the time you land on your final diagram, it has made it unambiguous what is going to be plugged into the left side of F net equals MA so that you can divide by M and get A, right? Or in some cases, maybe, maybe you're solving for other things, but that's the idea. And I'm going to say one last. So the idea is you draw a system schema first to know what are the objects that are exerting forces. Therefore, that gives you a bunch of lines that tells you, if you do it right, unambiguously what the forces are. Then you go to a next diagram, a pure free body diagram, to turn each one of those lines into an arrow, a vector. So now you have a rough sense of the magnitude, but you have a good sense of the comparative magnitude and a specific sense of the direction of each force. Okay, that's the pure free body diagram. That's stage 2. Then from the pure free body diagram, the thing that we're going to do today is you then start breaking up the vectors into their constituent components that lie along X and Y axes, so that then by the end, so it's 3 stages. By the end, you have a component free body diagram that literally has a bunch of arrows in it that are all pointing along one of 3 spatial axes. Like, they're all, every single one of the arrows will either be on an x-axis or a y-axis or a z-axis, or maybe you're using polar coordinates or something, but each one of them will know, in other words, all arrows will either be parallel with one another or perpendicular with one another, but nothing in between. So then, and this is what this is all trying to say right here, then you'll be able literally to write down F net equals MA for the x-axis by just looking at your x-axis of your picture and just putting in all the arrows that are going one way. You just put in as positive symbols, quantities, and then all the other ones that are pointing in the other direction on that axis, you put in as negative. And you just write that out for one axis, and then you write it out for the next axis, and then you write it out for the next axis if there are indeed 3. So summary of this whole thing, that's why the board is summarizing. This is all really, it's all still Galileo's principle of relativity to the day I come up with something else. It's till the day I die. It's all Galileo in the sense that it's form number 4 right now, that every single problem we're doing, every force problem that seems to exist in 2 dimensions is really 2 force problems happening independently, simultaneously yet independently on each one dimension. I didn't say that right. Every 2-dimensional force problem is really 2 one-dimensional force problems occurring simultaneously yet independently. That's what I mean by GPR form number 4. So that's why your goal is to get a component free body diagram. Your goal is to get a free body diagram that has all forces broken up into components lying along independent axes. And then whenever, okay, pro tip or whatever, whenever I write sine squared theta plus cosine squared theta equals one, whenever I say that, that is my shorthand or my summary. That's a way of saying two things at the same time. It's a way of saying Pythagoras. I mean, it's true. I think you know that but why do I care about that trig identity? Because that trig identity, if you really get used to trig, you'll notice what that's really saying. I'm talking about the second equation on the board right now. Sine squared theta plus cosine squared theta equals one is, if you really think about it, is the Pythagorean theorem for a unit circle if you regard sine as opposite over hypotenuse and you regard cosine as adjacent over hypotenuse. It's really the Pythagorean theorem in the limiting case of uh, of a right triangle whose hypotenuse is one. Put another way, that's my just clever, cute, like to me, that statement is a huge statement because it's really saying at the same time that the Pythagorean theorem is true and SOHCAHTOA is true. And so that's my way of, whenever I write that, it's my way of reminding you, we're now dealing with vectors. We're dealing with vectors. So it's all about resolving them and putting them back together, Pythagorean theorem and SOHCAHTOA. That's what that statement, okay? So I'm saying here, our goal is to draw a bunch of diagrams so that we get a bunch ultimately of vector components and trust that SOHCAHTOA still applies and Pythagorean theorem still applies and all that. And then finally apply each one of those components to one axis at a time. That's the program here. Okay, that's enough like theoret. And there's something in the chat, but I'm gonna now, I know that was like that's a big overview. Now I'm gonna go back to the homework and sort of skip around and finish problems there and apply it. Okay, I see the direct chat. Fine, thank you about the internet connection. Got it. Okay. Okay. So quick screen share, just so we're on the same page or in the recording. Right. Okay, so we're talking about this. We're talking about this homework, which is homework 7, I believe. You corrected me the other, maybe it's homework 8. You correct me again. I think it's homework 7. So, and I'm not going to do all of it. I'm just trying to, show you but we were in the middle of this Apple business, I believe. We had, tell me if I'm wrong about that too, but we had drawn a picture of the situation. We had drawn and again, let me say again too, this applies to physics 204 as well. 5-step method, which I'm noticing people are using in the exam. It seems like, thank you. That's really important, really good. 5-step method still lives with us for the rest of our lives. But whenever we get like really specific algorithms, which you sort of are like when I'm giving you specific procedures, which I am for Newton's law problems, like there's like a procedure. You draw system schema, you draw a pure free body diagram, then you break up and draw a component free body diagram. You can always consider those to be sub steps of step 4. Like like for Newton's law problems, step 4A would be draw a system schema. Step 4B would be draw a pure free body diagram. And step 4C would be draw a component diagram. And you could even say step 4D, and if anybody's writing this down and wants to submit it for a note screenshot, great. Step 4D, or if you want me to repeat it, if you just realize that I'm saying something fairly specific, you can ask me to repeat it. Step 4D would be take each vector component and turn it into a contribution on the left side of F net equals MA being applied to one dimension. Now I can't resist. I'm going to say again, when I wrote that on the board, I hope you see that what I wrote on the board is saying F net equals MA, the law, it's a vector equation. If we just write it as an equation, we put arrows over the F and the A to show that it's a vector equation. But what that really means in practice, if you take Galileo seriously, is it means that F net equals MA is true independently on each axis. So I get rid of this arrow and I put subscripts when I do it one at a time on each axis. Where do I get the information to plug in one at a time? I get it from a component free body diagram. If it happens, as is about to be the case now with this problem that we're going to continue, this multi-force warm-up, the one on the thing right here, I'll look in the chat in a second. This Apple thing, I'm going to finish it. I don't want to confuse you. This happens to be a situation where all of the arrows you see already from last week, all of the forces happen already to be on one axis. So there isn't a lot of vector work to do. That's good. So our life isn't like stressful. But you'll see as I finish it, that just means there's only one axis to deal with. It just call it the y-axis. So we're still going to follow this whole procedure. It's just that there's only one axis to deal with. So okay, but it's always the same procedure. Okay, so I'm going to go back. I'm going to unscreen this share. No, I'm going to unshare the screen in a moment. What I believe I'm up to, I'm going to look in the chat. Maybe someone in the chat is correcting me and telling me that I'm on the wrong problem. But I believe where we left was was right here. I believe where we were last Wednesday was right there. So that's what I'm going to go back to now and proceed. But let me just look in the chat. So I'm going to switch the screen. Oh, yes. Thank you, direct chat person. Okay, I'm going to repeat the steps. Yes, I think this is very concrete, helpful. Yes. And you should give yourself points, direct chat person, for a number, including please go back. Like that counts as a please go back portal points. So the steps that I just said for every problem involving forces, and this includes in Physics 204, which I look forward to seeing you all next semester. And if you take it on a Monday, on any class that involves a Monday, I'll see you in person and I'll look forward. Seriously, okay? When if you take, you get my point. And some of the sections are like half and half, like in person Monday, online on Wednesday. That's fine. That's me too, whatever. The steps are step 4A, draw system schema. Step 4B, draw pure, like from the system schema, like from every line in the system schema, turn into arrow and make pure free body diagram. So 4A, system schema. 4B, pure free body diagram. Step 4C, component free body diagram. Which apply, like, in other words, any arrows you see in your free body diagram that are like off on diagonals, and this hasn't happened yet. That's what I'm like sort of trying to get myself to here. But if you ever see any arrows that are not parallel or perpendicular to all other arrows, then you got to break them up into components from the methods like that you did with velocity and displacement, like in the last topic. So step 4A, system schema. Step 4B, pure free body diagram. Step 4C, component free body diagram. Step 4D, take each force component, plug it into the left side of F net equals MA being applied to one axis at a time. Like each arrow from your component free body diagram, you're going to plug into either net Fx equals MAX or net Fy equals MAY or like so, and then you're going to solve. I mean, you could say, I suppose, step 4E, do the computation and solve for whatever you're solving for, which is generally A. But that's the procedure. System schema, pure free body diagram, component free body diagram, take the components from your picture, plug them into the left side of one application of Fnet equals MA. That's the idea here. And the reason I just repeated that, well, somebody asked me to repeat it. But if you're one of those people who was like, I kind of got what happened in the first half of this course, but it was a little bit vague, and like I kind of got it when he was talking about it, but I never quite knew how to do it on my own. It always felt like there was a lot of decisions I was supposed to make to set things up. And if you felt that way at all ever, first of all, I'm with you. You're not alone. I felt that way too. Second of all, if you're thinking this sounds a little bit more concrete, why couldn't he just do this last time with the other topic? I couldn't. This is a little bit more concrete. I mean, the whole topic is not more concrete, but yes, there's a more concrete procedure for solving these problems now. There is, and that is it. The thing I just, so yeah, it's worth noting. Okay, thank you. Oh, and now there's more in the direct chat. Okay, I guess this is like a class. Hold on. Wait, yeah, yeah. That's a really good question. Wait, my chat seems to be frozen, but someone in the, so I might be missing something. Sorry, the chat is frozen, so I might be missing some, but one person in the direct chat is saying, and I think I know where she or he is going with this, is saying, wait, so in step four, they didn't say wait. So in step four, we have to draw a system schema and a free body diagram. So my answer is yes. Yes. For these kind of problems, like whether you call it step 4A, step 4B, yes. But if suddenly, so good question. If you're suddenly saying, hang on, I always thought like the diagrams went in step one. Why are we suddenly doing diagrams in step four? Good point. Good point. But here's why. And this was technically true of like vector problems, even without us saying it like recent. Like this is not actually the first time this has happened. But here's the real deal to everybody. Step one, we call it a diagram and it is, but it's really a picture of the situation. In step one, always, 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 right away when you're given a physics problem, you diagram the situation, the fact, the problem. You don't know anything yet. You haven't solved anything yet. You're not even trying to solve. And then in step two, you like state what the question is, right? So step one is diagram and fact pattern, meaning here's a, a fully labeled graphic illustration of the space and time relations of this thing. Hence, it's a physics problem, not just raw math. Then step two, you're like, so here's the question. Then in step three, just like in step three, you now say things that are true even before the problem started. Like, notice. I mean, now that you're getting more and more used to this, it's like a helix. Notice, everybody, in seventh grade, you might have said, write down what you know and then write down what you're trying to solve for and then solve. Yeah, sure, absolutely. But what we're now saying in physics is it's more subtle than that. In step one, you write down what you know. And in step three, you write down what you know. If you ever notice this, you write down what you know in step one and step three. But the big difference is step one is you're writing down what you know about this problem, what you were told is this experiment or this particular concern. And then in step three, you're stepping back and going, all right, so what do I know about the universe? What did I already know before I even walked in the door that might help with this problem? Like what law? And I will admit, some of the exams, I think there was a little bit of confusion about this so far, a little. So right, there's two different types of what you know about this particular, and then what you know in general. And then you put them together in step four to solve. Why am I saying that? Because a similar really good question that someone's bringing up is it's very possible, and in fact necessary, as physics problems get deeper, that we have more than one diagram going on. In fact, you had a whole bunch of vector diagrams going on in your past work. The distinction is that in step one, you're drawing a diagram of the problem, the question, the facts that are given. Then by step four, when you're now turning the crank and solving, now you start drawing diagrams that are actually solving the problem for you. That's why this is a perfect question. I'm sorry if I'm being redundant for some people in the room or that you just want me to get to the problem, which I will, but that's a really great like question. I mean, it may have even been an objection that was phrased very politely and respectfully as a question. What I'm here to say is, right, and I didn't understand that when I was an undergrad. I thought free body diagrams were kind of like step one thing, like just okay, here's the deal. Like, no. By the time you're doing a free body diagram, it is computation. It's just physical, visual computation. So yes. So my answer is yes. We're putting system schemas and free body diagrams and component free body diagrams in step four because they're freaking solving things for us if we do them right. I didn't mean to say free. Okay. Thank you. Okay. Well, and the person who asked that, you might want to acknowledge in the share. I mean, in the chat, if I answered the thing. But I'll go on now. But also, I see why it's frozen because of all this. Okay. I'm gonna switch to share because I think that's what's freezing everything. Hold on. Okay. Oh, yes, good. Thank you. So you both got closing the loop points. Thank you. All right. So now, and we still have 45 minutes. All right. I'm sure you're thrilled about that. All right. So I'm going to share. Okay. Okay. Um, okay. So back to And maybe someone in the chat tell me, I think this is called homework 7, but I don't want to tell me if I'm wrong. If it's actually homework 8 or something, please let me know. Or if you get a chance. It is homework 7. Okay, thank you. Thank you, Jocelyn. Ooh, and she went public. Thank you. Let's, there should be an extra points for that. Maybe there will be something. Okay, so all right. So in 3, it says draw a free body diagram. We already did the system schema, right? Now we're drawing a free body diagram of the apple. So I just draw a point that represents the center of mass of the mass that is the apple. And then every one of there were 2 lines in the system schema, 2 interactions, because there was Earth and then there was one thing touching the apple. So each one of those lines now becomes an arrow and it goes in a particular direction. We said this already, guys. So, but now they start getting labeled with their sort of technical labels. So we have a down arrow, which is the weight of the apple, like the Earth pulling it down toward it, right? And that from now on always is labeled mg. Now we discussed this Wednesday, right? From now on, the weight of an object is its mass times its the acceleration that it would have in free fall, right? It's like 1 Newton of weight is 1 kilogram of mass times 1 meter per second squared of acceleration. Like, oh no, sorry, take that back. 1 kilogram of mass times approximately 9.8 meters per second squared of acceleration from now on. Like if your mass is a kilogram, your weight is 9.8 newtons, or what we might generally often round to 10 newtons. And then you can convert that to pounds if you want to be American about it. But right? So weight is not M and it's not G. It's mg. Um, which is a multiplication from now on, right? Okay, so that's one force that's there. Then you got this other force, which is the, and by the way, so that weight is a pull. Now we've got this other force on the apple, which is a push. It's the table pushing the apple up. Why? Because the table is there underneath the apple, touching it. Like I'm not, there's no law that tables have to be there, but there is a table there. So it's pushing up. So it's a surface that is pushing against another surface like this, right? Like not like this, like this. So it's pushing. So there's a surface pushing perpendicularly to the plane of contact between the 2 surfaces. So the name for that is the normal force. We said that Wednesday. The normal force is the name for the component of interaction when one surface pushes against another surface. And by against, I mean perpendicular to the plane of contact. And the word in math and physics for perpendicular is normal. So we label this force with a big N, and I generally put like serifs on the end to distinguish it from, I do that on purpose so that if you just ever see me draw an N like a script N, then I mean newtons if I do that. But this, I mean normal. Okay, so we've got 2 forces. And again, I can't have, I'm going to go on, but normal does not mean that it's always there. There's plenty of free body diagrams that do not have a normal force in them. Plenty. And when they, anyway, but here there's a surface and it's, okay, so that's the free body diagram. Um, um, and I suspect that so those 2 arrows are acting in the opposite direction, and I suspect that they're equal in magnitude because I think the apple's sitting still. Um, okay, I'm gonna now. It says now normally if it didn't say anything further, if it just asked me to like solve for the acceleration or something like or solve for some force, I would then continue the procedure, and um start plugging those vector. I would go to step 4D. But there's a question here first, and it's a good question. It says write down the Newton's third law pair implied by each arrow in your FBD. Right? That's the question. And that's a really important question. So I'm going to dwell on it for a second. These two arrows that are in our diagram, they are opposite in direction. And I suspect, I believe, we're going to decide that they're equal in magnitude. That's why I made them the same length. So it's very, this now goes back to, I think I'm going to say his name because I think he did go public with this. This goes back, so I apologize if I'm wrong, to Muhammad's question from like 2 weeks ago or something. Like this totally would look like, and does look like to many people and to many websites, this looks like action reaction. I mean, there is an action here, and I mean, there is like two forces here that are opposite in direction and look equal in magnitude. So it's very easy to mistakenly believe that this pair here is a demonstration of action. It's not. The question is asking, well, what is the new, how does Newton's third law like apply here? And here's how. Sorry. Okay. Pair Newton's third law, pair one, is that since the Earth is pulling down on the apple, since the apple has weight, that means necessarily that's an action. The reaction is that the apple necessarily is pulling up on the Earth. And you really want to let that sink in and think about that. Like, not everybody understand, but go back to the system schema. There was a line connecting the Earth with the apple. They're having a tug of war. And there's no way. I mean, the whole idea of Galileo again, of Galileo principle, form number seven is that there's just no way I can pull you without you pulling me back. There's no way I can marry my wife on October 20th without my wife marrying me on October 20th. Literally, that's the concept. It's a reciprocal symmetric concept. Same thing here. If the apple is pulling up on the earth, if you want to call that an action, then the earth is pulling down. Sorry. If the earth is pulling down on the apple, then the apple is pulling up on the earth. It's a tug of war. It's just a matter of how you, and truthfully, to call one an action and the other reaction is just in the eye of the beholder. It's just in our mind. You could call it the other way. Because they're happening at the same time. So that's one pair. That's what Newton's third law. The law is saying the apple cannot be pulled down by the earth without it pulling up on the earth. And if there was nothing else in space, if there was nothing else in the world, they would just come together. That's it. Similarly, and so notice what I'm not saying is the fact that the earth pulls down on the apple does not mean that the table has to push up on the apple. That is not a reaction. The normal force is not a reaction to the weight of the apple. And a lot of websites will and books will really confuse you on this, or mislead you, or give you the wrong impression, or and whatever. Sometimes they're literally confused, but sometimes they're just like not, whatever. There is no law that says if I am acted on up, if someone acts on me down, then something else has to act on me up. If that were a law, if the up arrow in my picture were dictated by law to be there, that would mean nothing would ever accelerate. That's not what we're saying. Bottom line, I'm saying action reaction is on two different objects, not the same one. The action is one arrow in our diagram, and the reaction is somewhere else in some other diagram that we're not looking at, a diagram of the Earth. So similarly, then the other force, normal. So there's another pair, the one that's dictated by that arrow that says N. That says the table pushes up on the apple You notice this one's a push now. The first one was a pull, this is a push. They're totally unrelated. They don't both have to be there. They just happen to both be. Table pushes up on the apple. That is not English. Therefore, the apple pushes down on the table. It's always like that. If you were ever asked for an action reaction pair, you say you write out the action with a word like push or pull and with some direction like up or down or left or right or whatever. And then the reaction will always be that same verb. If the action's a pull, then the reaction will be a pull. And if the action's a push, then the reaction will be a push. And if the action is up, then the reaction will be down. It's always like a tug of war or like a sandwich. Okay. So there's, in other words, bottom line, I'm going to move on. There's two forces in this diagram. They are not, even though they're equal and opposite, they are not Newton's third law pair. Each one of them is half of a pair. Every force you ever see in a free body diagram is one half of a pair, the other half of which is in some other diagram somewhere. That's what we're saying here. Otherwise, nothing would ever accelerate. Okay, so that was four. Okay, that's the answer way. I'm going back. Sorry, I'm just, and then, oh, I think, okay, then five. Okay, five is what I believe we figured out, didn't we? Yeah, five, we've sort of, I'm going to do five. Oh, well, okay, hold on. So then five is it's basically saying, it's asking, what's the weight of the apple? Well, we figured this out, or with height, we figured this out last week. Weight equals mg. So if the mass is zero point 0.5 kilograms and g, whenever you're not in the lab, if you're doing this like homework or exams, you can always round 9.8 to 10. I promise. And it's not because I'm being nice to you, like everybody does that. Um, so the weight of the apple is approximately 5 newtons. Um, and then six is asks for us to compute the normal force, which I'm about to do in a second. I'm just switching screen. On my side, switching screens to the chat. Hold on one second. Okay, nothing in the chat. Okay, so question six, what's the normal force? So now this is gonna be our first example, even if, whether you think it's easy or hard, this is like our first example of like actually now following my algorithm. Like we've done the diagrams. We're now going to take the purpose is we're going to take the arrows from our diagram and um, and plug into F net equals MA. So technically, I'm about to do like step 4D, but I'll say, since we've never done this before. Okay, to be as explicit as I can. We did step 4A, that was a system schema. We did step 4B, that was a pure free body diagram. Now we have this pure free diagram, we have a pure free body diagram, which is this diagram right here. We look at it. We look at it. If there were any off-axis vectors in that diagram, like any diagonal lines, any arrows that are somehow not parallel or perpendicular to every other arrow, then we would proceed to step 4C, which is we would zoom in, and we'll do this together. It's just like not necessary for this problem. We would zoom in on individually on each off-axis vector, and we break it into its components, like using SOHCAHTOA, right? And then we make a new diagram with just those components in it instead of the hypotenuse. And from there, we would proceed to step 4D. Now, what I'm saying here is, okay, we have the luxury of a comparatively simple problem, straightforward problem. So there's nothing to break up. All the arrows are already parallel with each other. Okay, so this is our component diagram. So I'm going to proceed to step 4D. I'm sorry. Oh, no, that's right. Yeah. Okay, so I'm going to use that diagram to proceed to step 4D. I'm literally going to solve F net equals MA now. I'm going to take, and it's in this case, so step 4D, we could say. I'm going to say the sum of all the forces acting on the y-axis equals the mass times the acceleration along the y-axis. Right? If this were a more complicated problem, I would also write this down for the x-axis and possibly the z-axis, and I would like proceed individually on each axis. There's only one axis here. The reason I'm dragging this out now, it's okay, we have 28 minutes. The reason this is like the key here now, like this is where all of our pictures turn into math. And again, I can't emphasize enough. I think this is what everybody often like really is craving in physics is like something to get you to set up the math. And what I'm claiming here is it's the pictures. So, so, so I look at the y-axis. I'm going to take every single arrow from that axis, and we're going to take the label on every arrow, and I'm going to put that label on the left side of F equals MA. Only I'm going to be careful to distinguish direction. Like anything that's anything that's pointing up, I'll call positive. I should have made this decision right from the start. Anything that's pointing down, I could call negative. You could do something different if you want, but just be consistent. So I'm literally going to say, okay, I'm adding up so sigma means sum of, add up all the forces. So we've got the normal force, and then we've got the mg force. I'm adding them together, but the mg is going in a different direction. So it gets a minus sign. Like, so technically what I'm really doing, I'm just gonna do this once easy. What I'm really doing is going like this. And that's what I'll always do. Do you see right? So I don't have to do the thinking. If the diagram is right, there's nothing to think about. Anything that's going one way gets a positive. And if there was a bunch of forces here, like there are in the lab and stuff, a bunch of forces going one way, they would all get plus signs. A bunch of forces going the other way in the axis, they would all get negative signs. And all of them together make MA for that axis. Once you get it, like many of you probably do, then you're like, move on, move on. Like once you get it, it's so self-evident. But until you get it, it's all a big mystery. So I don't know. So okay, so here it is, right? Now that's my statement. And by the way, please notice also, like the step 3 of all of this, one of the step threes, the GDP is F net equals MA. Like that's the principle that we're using here. Notice I've just now started expanding the principle. I don't even freaking know what I'm solving for at this moment. Like frequently it's acceleration. In this case, it happens not to be acceleration. It doesn't even matter what I'm solving for. That's my statement. But now it is asking me to solve, right, for the normal. It's asking me to solve for n, right? Like here, where I'll just write. I mean, here, we're solving for n. So, so I'll isolate n. In other words, so n equals MAY plus MG. Like, right, I'm solving for n. Okay. But now I can start plugging in. This is all step 4. It's kind of computation now. Now I know things, so I'm going to start plugging in. In other words, A sub y in this case, now be careful. Like the rate at which this mass is accelerating along the y-axis. I don't mean g. G is the rate at which something would accelerate in free fall. That number is always 9.8, roughly, whether something's free falling or not. G is G, right? But this first term is A. This first term is A sub Y. That doesn't mean G. That means what rate is this object actually accelerating? Often that's what we're solving for. Here we already know. And I hope you join with me in understanding that the acceleration here in this case of this object along any and all axes, particularly the y-axis. Actually, I'm going to put, what is the accelerate? It's not a trick question. I'm just making sure we're all together. It's not meant to be a trick question. I'm going to, in the chat, in direct chat, please, and for points, just write down what is the acceleration? And you do know, what is the acceleration of this object, of this apple, in this case? Please put in direct chat. I'll wait till I get 3 responses, right or wrong, and then I'll move on. But in direct chat, please put down what. Awesome. That's 1 and it's correct. Awesome. That was public chat, but okay. So awesome that that's an answer. I'm not going to say if it's right or wrong because it's public. And then there's another one in the direct chat. Okay. No, it's okay. It's totally fine. No, it's enthusiasm. No, it's fine. But okay. So and I agree. Great. Okay. So now I will admit with all respect, there's someone in the direct chat that just sort of proved to me why it's worth me asking this question. And no shame, total respect to the person in direct chat who just put an answer. So a lot of people would often think it's 9.8. No, the G is 9.8. G, like the rate at which something would free fall is 9.8, and that is relevant to this problem. But the rate at which this thing is accelerate is in fact 0, as many of you, including Nadine and Mohammed, are saying. It's 0, and I'm saying this because it's a pitfall. It's a trap. It's a checkpoint trap. Whatever. First boss. Like, if you don't get what I'm saying, tell me later privately and we'll talk about it. But basically, what I'm saying is here in this case, A sub y is 0. G is not 0, but A is 0. There's the rate at which. Okay, you get my point. I think. Therefore, we plug in. Like, this is our statement. Whoops, sorry, no, it's not. This is our statement, but I'm saying this happens to be 0, hence what I'm saying is the normal for, I'm saying in this case, first of all, this is just a little practice. I'm not saying it's the hardest problem in the world once you get used to it. And some of you may want to be seeing the harder ones, but this is the procedure. If you really understand the ins and outs of this procedure for this kind of problem, then you extend this procedure no matter how hard the problem is. Like, no matter how many forces there are, this is what you do. So just notice what I'm saying. I'm saying we set up F net equals MA. And then by setting up and then plugging in the arrows from our diagram into F net into the left side, okay, we end up getting the statement N equals MA plus MG. That's not, don't memorize that. That is not a step three. It's not a principle. It's just a result for this problem. But in this case, it happened that we weren't solving for A, we're solving for N, but we knew A was zero. So we cross out that whole term. And what we find here is that N equals MG. In this case, the normal for, so this is what verifies why it was correct that my two arrows were the same length. Now, please notice, I'm yelling so you can tell it's important. Please, please notice, N equals mg is the answer in letters to this problem. And then if we plug in for m and g, we get 5 times 9 times 10 meters per second. So we get 5 newtons. I mean, we get 0.5 times 9.8. So we get 5 newtons. I'm saying in this case, the upward normal force exerted by the table does equal the downward weight of the apple. That is true. That's the answer to this. But what's really important is how I got that answer is from Newton's second law, not Newton's third law. That's why we paused in the middle of the problem to look at Newton's third law before we did this. I cannot emphasize enough, and this is where I'm all for the web, and I'm all for AI, sort of, not at all really, but kind of sure. I'm all for whatever resources you have in the world, but I'm telling you right here, this is a pitfall that will get you into trouble if you just trust. If you don't think it through and trust, and instead you just trust the world, what I'm saying is the normal force is not always equal to the weight. There is no, you'll think it, people think it is, but the normal force sometimes isn't there at all. And sometimes you'll see, like in the lab 5, the normal force doesn't equal the weight. It equals something that's related to the weight, but it ain't the weight. Don't memorize what I just wrote here. This is not a step 3 or a law or anything. And it's definitely not Newton's third law. What this is an application of Newton's second law. Bottom line, what I'm saying is, oh yeah, when something just sits on a table, yes, the upward normal force exerted by the table equals the downward weight of the object, not because it has to, but because the thing is just sitting there. So that must mean that whatever is being pulling down on it must be balanced and supported by whatever's pushing up on it. That's why the darn thing isn't moving. But even right now, and this is the next problem on the sheet, and we're going to, and it's 1022. But if I go like this with a pen, the only way I could do that is, is if there's two forces, the downward weight of the pen and the upward normal force of my hand. When I go like this, there are those two forces, but you better believe the normal force ain't equal to the weight of the pen. The normal force is greater than the pen in this case. That's why the pen is accelerating up. So F net equals MA. And the normal force equals whatever it has to equal if it's there at all, in order for all the F's together to make the A. If the A is 0, oh yeah, then some forces are balanced. Okay, that's the lesson of that. But that's how to do Newton's second law. Okay, we have 18 minutes. Let's go on. I'm going to skip. I'm going to start skipping now. Part B is exactly that same problem. Part B. Okay, I'm really quick screen. Yeah, okay, back to quick screen share. Just so we know where we are at for something. So we just did that. Okay, this part B right here about the crane lifting, it's exactly what I just said. And it's exactly the same problem, and you would do all the same physics, all the same diagrams, all the same equations. You would end up again with N minus mg equals ma. If you were to do this part B, okay, you would again end up with N minus mg equals ma. The only catch is that here a wouldn't be 0. It would be 3. And if you're calling up positive, which is a wise thing to do in this case, then it would be positive 3. So you'd have N minus mg equals ma, but for a you'd plug in, so therefore N would equal mg plus ma, and the a now is not 0, it won't drop out, it will have a 3 times m, and m is 450. So you'll find here, that so I'm literally giving you the answers right now. So for B, okay, just so we're on this, and stop me if I'm going too fast or something. like the pictures are all the same. Literally, the pictures are the same. I mean, literally, there's not. Oh, and I should pause on that. Even though this thing is now accelerating up, so it seems like a different situation, the forces acting are the same forces. An upward force of, um, maybe, well, it's lifting. So this would be a tension from the crane. It'd be a capital T instead of an N because it's like pulling rather than pushing. Okay, so I would call it tension, not normal. But then but it's just two forces. That tension that's up and the mg that's down, and there won't also be a normal force or something like that. So then the statement would be T minus mg equals ma. So therefore, and when it says in question 4, compute the force that gravity exerts, that's again asking what is mg? Well, it's literally 450 times 10. It's 4,500 newtons. That would be the answer to 4. 5, what's the force that the crane exerts on the scrap metal? I would call that tension. In other words, now it's solving for T, just like we were solving for N in the last problem. So T would equal mg plus ma, but ma is not 0 now. So, I mean, mg is 4,500. Ma would be 450 times 3. In other words, 1,350. So the answer to this one, right? Yeah. So the answer to this one would be 4,500 plus 1,450, or if I did the math, or 1,350. And you add them together and you get an answer. In other words, in this case, if the thing is going up, the tension isn't just supporting the weight of the object, it's doing more than that. It's literally pulling the object up. Okay, so that's the idea. So that's how you do that problem. Then what's going to happen with this whole duck elevator thing? I'm looking, is there anything in the chat? The duck elevator is a deep dive into that same concept. It's just what it's really trying to get you to see all these problems is how the normal force works. And it could be and and the answer is it does whatever it's supposed to do to make to obey Newton's second law. It's trying, okay? I don't want to overstate it again. So the elevator thing, and even a duck in an elevator, it's also trying to get you to realize if an elevator is going up or down, or if an elevator is doing something, what you don't want to do is start introducing magical forces. Like a lot of people, it's for the summary of this duck elevator thing is the duck is standing on a scale on the elevator floor, or is it a scale? No, just standing on a floor. I'm just looking. Yeah, yeah. The duck is just standing, um, on the floor of an elevator. So at any moment you draw a free body diagram of this duck, again, you're just going to literally say, well, there's the mg down of the duck because the earth is pulling on it, and there's the upward force of the floor because the floor is touching the duck. And that's it. Like, and how do you know that from the system schema? In the system schema, you always put in the earth, and then you always only put in any object that's touching every and any object that's touching your mass. In this case, that's the floor of the elevator. In other words, so you'll put in a normal force up, you put in an mg down, and then the elevator is doing different things. So that will adjust, that will create different values of A that you'll plug in through the problem, just like we did a second ago. What you won't do, the real purpose of this elevator problem is what you shouldn't do, what you might be tempted to do until you get used to this, is never put in an arrow that's like the elevator force or something like that. There's no such thing. All the system schema is there to force us to see that. That in the system schema, always you draw Earth and then you just draw anything that's touching your object. That's it. So when you're standing in an elevator and you accelerate up to the fifth floor of of the new building, whatever, what's bringing you to the fifth floor? The floor of the elevator, because that's what's touching you. That's what's shoving up on your feet. There's no right. The cable of the elevator or the electronics of the elevator, what they're doing is something to the floor, maybe. If you want to draw a diagram of the floor, then maybe if the cable is touching the floor, okay, that's a different physics problem. But we always only draw Earth and anything that is directly touching a mass. That's what the system schema is trying. And if you do that, you'll never make up forces or you'll never leave out forces. You'll be clear on what's going into F net equals ma. All right. So that's just a summary of the elevator of the duck thing. I mean, again, you can email me or maybe I have solution sheets somewhere or maybe an old video, but like, um, I, we could talk if you want to drill down on that, or if I catch something in your homework, I'll let you know. But that, okay. So I'm just, I'm just scrolling through to see if there's anything more. Yeah. So reflection. Oh, yeah. Part C, I'll say this quickly too. It's 10:30. Okay. In part C, now the elevator, I mean, excuse me, now the duck is like standing on a scale. And this is something we actually used to do in the lab in this class, and maybe if you ever were to, you can take a bathroom scale and bring it with you into an elevator. It's kind of fun, kind of. Um, and you'll find if you stand on that scale, like while the elevator's sitting still, the scale will register your what you expect your weight to be. And then and then when the elevator starts going, once the elevator is cruising, once the elevator is moving at a constant velocity and you don't feel anything in your stomach and you don't feel weird or whatever, right? That whole Galileo principle thing, then if you look down on the scale, it'll continue to register whatever you think your weight is. Okay. But then you'll notice when the elevator floor is accelerating up or accelerating down, and let me be very clear, accelerating up could mean moving up while speeding up, or, for example, or moving down while slowing down. Both of those would be a case of the acceleration vector pointing up, right? When that happens and you feel something in your stomach, right? Because now, right now, F net equals ma is like now there's Newton's second law is kicking in. It's not just Galileo's principle anymore. When you feel something in your stomach, if you were to look down at the scale, you'll actually notice the needle says something different from what you expect. If you're accelerating up, the needle will say that you are heavier than you normally think you are, than you typically think you are. Right? And if you, right? And it's not crazy. What's going on there? What's happening when you stand on a scale is you're pressing down on the scale. By Newton's third law, the scale is pushing up on you. Let me say it the other way around. The normal force from the scale is pushing up on your feet. By Newton's third law, your feet are pushing down on the scale. The needle responds to springs. And so you're pushing down on springs in the scale, even if it's electronic. There's springs, you're pushing down on them. The needle is telling you how much the springs got compressed. So what the scale is really measuring is not mg. What the scale is measuring is n, the normal force between you and the between your feet and it. Like it is pushing up normal force on your feet, but by Newton's third law, you're pushing down on the scale. So that's an action reaction pair that have to be the same. So what the needle is saying is how hard are you pushing on that scale? Well, when you're accelerating up by the logic that we're saying here, when your A is not zero, then your N is greater than your mg. So the scale doesn't know what Earth is doing. The scale knows what it's doing to your feet or what your feet are doing to it. So bottom line, what the scale will ever read, assuming the scale is reading in metric units like newtons, right? And then you could convert those to pounds if you want, or back and forth. The scale does not, if you're to write anything down to summarize what I'm saying right now about all of these duck problems and everything, the bottom line is scales don't measure weight directly. Scales measure apparent weight. Scales measure normal force. And the normal force can be changed by acceleration. So scales, your weight is still your weight. Your mg is still your mg. But what the scale will tell you is your n, the normal force. And your n will be affected by A. Take it to the extreme. You've heard this before. If you were to cut the cable in the elevator, I mean, quark forbid, so that you're now in free fall. If you were in free fall, think about it. The scale would not be pressing on your feet at all anymore. You'd be falling at the same rate that the scale would be falling. There'd be n minus mg equals ma. A would be the same as g if you're in free fall, right? So it'd be n equals mg minus mg, right? So if you're in free fall, the scale won't press on your feet at all. You won't feel anything, and you'll be registered as weightless. Like your weight, according to the scale, will be zero. It's not literally zero because the earth is still pulling on you, but there's nothing to resist that pull anymore. That's what happens to astronauts in satellites in orbit. They're just in, it's not that there is no gravity out there, it's that they're in perpetual free fall. It, and that's right. So if they pour a drink, the soda does fall down, but so does the can. And so do they. So it's like if you were falling off a building and you tried to pour something, it's not that it wouldn't pour, it's that everything is pouring. So everything stays together. So it's a sensation and experience of weightlessness. That's a lot, but bottom line, the normal force is what a scale measures. Okay, it's 10:35. Okay. So that's like my summary of all that stuff. Now, what we have to get to, and we will get to more and more for this Wednesday, I want to start getting to like this stuff here. I want to start dealing with friction, and I want to start dealing with angles, which is of particular importance. So obviously I'm not going to get very far today. Maybe I'll just keep summarizing for a second, but it's 10:35. Yeah, I don't want to get into the weeds with 5 minutes left, but so what we have to deal with now is like really start breaking these forces up into angles, and we have to start really dealing with the intricacies of friction. Oh, I know what I will say with 4 minutes left. In the chat, please tell me, where are you in terms of Lab 5? I believe you started it, but you still have another week of it left, and the formal reports are not due for a while, right? Like my ultimate goal with all of this is to help you really write a good formal report for Lab 5 and understand Lab 5. So just tell me so I've got 4 minutes left, but just tell me in the chat, have you started Lab 5? Are you in the middle of Lab 5? What's the story?
We're done with lab 5.
You're done with Lab 5.
Yeah.
Wait, you made a prediction, you took all the data and you analyzed everything? Wow, okay. But okay, your report is not in though. Yeah, I hope, I think. Correct. I mean, you have
No.
okay. So my goal is to help you with your report because that's a big one, Lab 5, just like Lab 4 was. Oh, you finished Lab 5? Wow. All right, good for okay. So first, my goal is to help you with the post lab. Then I guess. All right. So by Wednesday, I know we're running out of time today. I promise you that I'm going to get into the intricacies of the friction and the angle. I mean, I'm glad you, and we'll talk about it like Wednesday, and we'll keep talking about. So okay, blah 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 blah. I'm glad you told me that. The one quick thing I'll say right now, with 3 minutes left. Okay, that's you know what? I was gonna say one more quick thing to I'll say it in English, but I don't want to keep you late. I do it too often, and I don't want to like crowd your brain with some big new. So I'm just going to say one thing where we're going to go with friction on Wednesday. What I think you sort of already saw in the lab, but I'll say it my way. When two surfaces are rough, when two surfaces are rough, and they press like this causes there to be this, right? Like I'm saying, when surfaces are rough, they lock into each other microscopically. So the more you go like this, the more hard it is, the more you press them against each other, the harder it is to rub one or slide one across the other. I've been saying that in English. So I'm saying in English, the friction force between two rough surfaces, it turns out to be approximately directly proportional to the normal force between two forces. Friction is directly proportional to the normal force. The constant of proportionality is the roughness of the surface, what we measure as the coefficient of friction. I, so whenever you've seen the equation on the web or in the lab, or what we're going to expand on Wednesday, if you've ever seen the equation F equals mu times the normal, that's what we're really saying. We're saying like y equals mx plus b, but b is 0. We're saying like one thing is proportional to another. If you were to graph how hard you're pressing two surfaces on this axis versus how hard they are to rub along this axis, you'd get a straight line always. And the slope of that line is literally how rough they are. If they weren't rough at all, it'd be a horizontal line. You wouldn't ever get rubbing or sliding friction. But the rougher they are, the steeper that line is. So friction equals coefficient of friction force equals roughness coefficient times normal force. That's what that means if you've seen it, and that's why. We're just saying the harder you go like this, the harder it is to go like that, given the roughness of the two surfaces. But we'll leave it with that for now. Your exams are coming. You are very patient. You are very smart. You are seriously, you're very active. I totally see it. I appreciate it. To be continued. See you Wednesday.
Thank you, Professor.